Okay, so bit of TOK here, or a bit of maths actually. 3 ways to try and prove that there are 180 degrees in a triangle. So my conjecture, the thing that I'm hoping I can try and prove, is going to be the following. Conjecture. Interior angles in a triangle are equal to 180 degrees. I'm not a mathematician, so forgive me if my maths is terrible, but hopefully the basics here are going to be okay. So method 1, let's try that out. Method 1, measure the angles. So here we go. Unfortunately, middle of the lockdown, I have pretty much no mathematical tools. I've managed to find some scissors and make a triangle. I'm going to use my fake lockdown protractor to measure the angles. So nice manual way of doing it. I suppose the axiom I'm starting with, what I'm assuming to be true, is that in my protractor, my circle, there are 360 degrees. That is my axiom that I'm going to try and use to prove that triangles have 180 degrees in their interior angles. So let's measure the first one. I'll be a little bit approximate here because I'm using a paper circle. Okay, angle number 1, let's call that 40 degrees. Angle number 2, let's call it about 110 degrees. Angle number 3, let's call that one 30 degrees. Let's add those up. 150. Oh, look at that. Beautiful. 180 degrees. Is that a perfect proof? Well, we'll think about that in a minute. Is there a chance that I'm probably making some measurement error here and that those values are not perfect? Almost certainly, but that in a very basic way is some evidence that there are 180 degrees in a triangle. However, that is just for one triangle. If I wanted to prove it and get rigorous proof, I would have to do that for every possible triangle. So pretty much an infinite number of triangles, which I think you would agree is impractical. So there's one way of trying to do it. It's not giving me rigorous proof because realistically, I'm not going to be able to do that for all possible triangles, but it's some kind of evidence, maybe giving me a bit more confidence in my conjecture, but I definitely could not turn that conjecture into a theorem. Let's try a second method. Okay, method 2. I'm going to use a bit of deductive reason here. And first of all, I'm going to use my lockdown ruler. I don't even have a ruler in this place, to draw a nice straight line. And my first axiom that I'm going to use in this case is that a straight line has 180 degrees in it. So there's my straight line. Let's get my triangle back out. What I'm going to do, I'm going to rip off, in fact, let's just mark these little angles here. I'm now going to rip off each of those corners. And hopefully, if I arrange them nice and neatly down here, they are going to end up with that serious precision. It's a beautiful thing. There we go. Those 3 angles, when I put them next to each other, actually fit that straight line pretty nicely, suggesting that if there are 180 degrees in a straight line and those 3 angles lie next to each other to fit on that straight line, therefore my conclusion would be there's 180 degrees in the interior angles of that triangle. However, same problem as method 1, actually to get rigorous proof, and prove it for all possible triangles, I'm going to have to do that process an infinite number of times, which practically is nonsensical to do. So again, it's given me, perhaps you could call it some kind of proof, some kind of evidence, but it is not giving me rigorous proof. So let's take those away. Now this third method hopefully is going to be a little bit more interesting. Method 3, we're going to now introduce a second axiom. So I'm going to use the straight line 180 degrees axiom from before, but I'm going to talk about the axiom of transversal lines. Now, I'm not a maths teacher, so I'm not going to go through this whole explanation because I'll probably make a mess of it. Here we go. Let's draw a triangle. We're now going to go into the realm of the kind of theoretical. Bam, bam, bam. Done. Let's call that angle A, B, C. Sorry, terrible pen. Now, transversal lines, something like drawing parallel lines. Of those different points, and then one down here, and like that. And then starting to use this second axiom here to say that, okay, angle A, that angle B is going to be there, angle C is going to be there, angle A is going to be there, and then vice versa, something like that. So if I look along my straight line here, just kind of like the example we saw before, if I take that as a straight line, A, B plus C are perfectly fitted to that straight line. Same way I could look underneath it, C, B, A, perfectly fitted to that straight line there. Now, the interesting thing about this third method is that given that this is a theoretical triangle, it doesn't matter how I change the angles inside that triangle, the same theory applies. I can use these axioms and I'm going to get that same result every single time I do it for every single possible triangle. So I do not need to repeat that for an infinite number of triangles, because actually this theoretical triangle ABC, those could be any numbers, and this is still going to be true. So in this case, method 3, we now have rigorous proof because we've proven it for all possible triangles. And that is the whole kind of aim of maths. Now, once I'd done that and other people had kind of had a look and checked my thinking, this conjecture, we could now consider a theorem. Remember, that is not theory. Theorem is something that has been rigorously proven. That's kind of the holy grail for maths. You might even compare it to something like a law in the natural sciences, something that we are kind of have the greatest confidence about. And that is a little bit of maths and a bit of TOK, and we will leave it there.